Hello and welcome back. Today I want to talk about using transistors in switching circuits and the various types of losses that occur in such a situation. Normally, the choice of component in a circuit relies upon multiple factors, like size, various electrical parameters, ratings, price, but also performance. When it comes to a switching circuit, like a power supply or a power amplifier, one of the key performance criteria is efficiency. So it's quite important to know how your choice of transistor will impact the overall circuit behavior. So today I will be looking at the main loss mechanisms that occur in a MOSFET type transistor used in switching applications. So if you're curious, then keep watching. Now, the main reason for choosing a switching circuit over a linear one is efficiency. The switching circuit is usually more complicated, more noisy, more difficult to build and operate correctly. But it's all worth it, since the power dissipation can be a fraction of what the equivalent linear circuit would generate. One key aspect of keeping the efficiency high is keeping the switching transistor operating with minimal losses. To that end, there is not one unique loss mechanism to consider, but many. Some types of loss are unavoidable, and others are application dependent. So let's take things one at a time. First loss mechanism to consider is the most obvious one, the conduction loss. So this occurs when the transistor is conducting current. Now, based on the exact circuit type and load, there is a certain amount of current running through the transistor when the transistor is on, so when there is sufficient gate voltage. Now, since the transistor is not perfect, it has some on resistance, which is usually documented in the datasheet, and therefore when this current is passing through the transistor, there is a certain amount of conduction loss associated with the product of the current and the on resistance. Now, there's not much you can do about the average current that passes through the transistor. That's the whole point of having a switching transistor. However, you can reduce this type of loss by choosing a transistor that has a lower RDS on value. To illustrate the various loss mechanisms, I will be using a set of SPICE simulations, and to keep things simple, let's start by modeling the switching transistor as a switch. And to highlight conduction loss, we only care about the on resistance of the transistor. So in the datasheet, this is found as a drain source on resistance. To highlight the impact, I prepared two circuits, which have the same input signal, output load and supply voltage, but the difference is that the two switches have different on resistance. So the left one has a 100 milliohm value, the right one has a 1 ohm value. So if we now run the simulation, we can plot out our input signal, add another plot plane, and then look at the power dissipations on the two transistors. So we are getting some spikes right at the transition point, so this is because the simulator is not simulating an instantaneous transition. However, if we zoom in, as we can expect, the power dissipation occurring during conduction is much higher on the red trace, so the one attributed to the S2 switch, the one with the higher on resistance. So as expected, the loss is proportional to the on resistance. A higher value of on resistance will lead to a higher conduction loss. Now let's continue with gate charge loss. So this is the loss associated with turning the transistor on and off. So the transistor's gate behaves like a capacitor, and every switching cycle, this capacitor needs to be charged to a certain voltage to turn on the transistor, and then it needs to be discharged to turn off the transistor. And while the previously stored energy in the capacitor gets turned into heat. Now, even though this loss is not occurring on the transistor itself, most of it is dissipated on the driver, it can still be a significant quantity of loss. So it's important to consider. The main parameters impacting this type of loss are the gate capacitance, the voltage to which the gate is being charged and then discharged from, and finally the switching frequency, how often is this capacitance being charged and discharged, since this loss is occurring at every switching cycle. To model this behavior, I made a copy of our first circuit, kept the same switch model, but I added an equivalent gate source capacitance, so 1 nanofarad. If we run this simulation and we compare the power dissipated on the two switches, they're more or less identical, so the power dissipated on the switch itself did not change. However, if we look at the power dissipated on the series resistor, here we do see a difference. So with our initial resistor there was no power dissipation in an ideal circuit. However, with our second circuit we do have a non-neglectable amount of power dissipation. So if we now look at the input signal, we can see that this dissipation is occurring exactly at the transition moment, so either when the input signal goes from low to high or from high to low. So the loss occurring on this series resistance, which in real life is comprised of the internal driver resistance, the internal gate resistance, and, well, any resistor placed in between, can become quite a significant amount of loss depending on how large this gate capacitance is. So far, we looked at losses that will never go away, regardless of use case or circuit. The conduction and gate charge loss will always exist. You cannot prevent these, only reduce them by component choice. Let's now look at other loss mechanisms that are not always there, or at least not to the same extent. First is output capacitance loss. So this is related to the output capacitance of the transistor, which, depending on the use case, may be charged to a certain voltage when the transistor switches on. So if there is a voltage there and the transistor is switched on, the capacitor is discharged by the transistor. This occurs at every turn-on event. So for a basic resistor load use case, this loss will obviously occur. But in some circuits, you have the principle of ZVS, zero voltage switching in place, where the load is resonant, so that the drain voltage passes through zero when this transition occurs. In that case, this loss is not occurring. So this particular type of loss depends on the output capacitance of the transistor, the drain voltage at the moment of transition, and the switching frequency. Now, it might be important to mention at this point that the output capacitance of a transistor is comprised of the drain source capacitance and the gate drain capacitance, both of these normally being present in the datasheet. But for simplicity, I will only be using a single capacitor in the equivalent model. So I took the previous circuit that only had the resistive load and added this extra capacitor, and if we run the simulation and compare the two, so first of all we have the power dissipated on the old circuit and the power dissipated on the new one. So we can see these extra spikes appearing, so these blue ones, which are much larger than anything that was present on the old circuit. And if we zoom in a bit, we can see that these are appearing only on the rising edge of the input signal. So when the transistor is switching off, the capacitor gets charged through the load. There is no loss associated with this. But when the transistor is turning on, then this capacitor gets discharged through the switch, hence this extra power dissipation that is appearing. Now we can look at a different circuit which does present ZVS, zero voltage switching, like the current switching class D amplifier, which I looked at in more detail in a previous video. So if we run this circuit to observe its behavior, so I already added this extra output capacitance. If we look at the moment when the input signal is transitioning, so in green we have our input signal, we can see that the voltage present in the drain of our transistor is almost zero. So we have a sinusoidal voltage waveform which goes through zero right at the moment of transitioning, hence the zero voltage switching. Because of this, if we now look at the power dissipated on the switch, we do see some small spikes appearing right at the moment of transition, but these are nowhere near as bad as if the voltage would be higher at this transition point. So this is a far less wasteful situation than our previously analyzed circuit. Next, let's look at switching loss. So we had switching related losses before, but this one in particular is caused by the non-instantaneous transition of the transistor. So when used as a switch, the transistor is operated either as an open switch with infinite resistor when there is no current passing through it, or as a closed switch with a very small resistance when the current passing through it is maximum. However, in between the two states, the on and the off state, the transition is not instantaneous. So it takes some non-zero amount of time to go from one state to the other. And this is where this particular type of loss occurs. It appears both at turn on and turn off, and it can only be prevented if you achieve both ZVS, zero voltage switching, and ZCS, so zero current switching. Only if there is no voltage on the transistor and no current passing through it at the moment of transition can this loss be prevented. So it's not that easy to get rid of this. So this type of loss is dependent on quite a few parameters. So on the one side it's dependent on the drain voltage and drain current of the transistor during transition, and well, the switching frequency, since this occurs at every single switching cycle, and is dependent on the exact time the transition takes, which is influenced by the driver resistance, the transistor threshold voltage, the peak gate voltage that is being achieved, and the gate source capacitance. So all of these 4 parameters, to an extent or another, will influence how fast the transitions occur. So to look at this phenomenon, let's go back to the current mode Class D amplifier. We already saw that this type of configuration has zero voltage switching, so losses should not occur because of the equivalent output capacitance. However, in this application, the switch is still switching current, so the speed at which the switch will be transitioning will have an impact over the power dissipation. To highlight this, I prepared 2 circuits in which the difference is the driving signal. So one has a 2 nanosecond slope, the other has a 10 nanosecond slope, so it's much slower. And the switches are implemented with a negative value for hysteresis. So the transitioning between on and off states is not instantaneous. So if we run the simulation, so first of all we can look at the 2 driving signals. Let's just zoom in a bit. So in green we have the fast 2 nanosecond signal, in blue we have the slower 10 nanosecond slope signal. Because of these transitions, if we now look at the currents passing through the switches, again we see a similar story. So the fast switching switch has a fast current transition, the other switch has a slower transition. And because of this, if we now look at power dissipation, maybe just zoom in a bit further. So in pink we have the fast switching switch, we have power dissipation during the transition, but it's relatively small. However, for the other switch, the one that is transitioning slower, we have a far larger area of power dissipation associated with this transition. So the slower the transistor is switching, the higher the power dissipation that is occurring on it. Now, one other notable example here is the Class E type RF amplifier. So I will be analyzing this type of circuit in more detail sometime in the future. However, the interesting thing about this circuit is that since the transistor is driving a resonant load, so let's just pull up the various waveforms. At the moment of transitioning, we have almost 0 volts in the drain, so we do have 0 voltage switching on both slopes, so we're not getting losses from that. And if we look at the current running through the switch, maybe just zoom in a bit. So we are getting some spikes, but other than that, the useful current that is going through the switch, at least at the turning on transition, is almost 0. So for the rising edge of the input signal, we are getting both 0 voltage switching and 0 current switching. And for the turning off phase, well, we do have non-zero current, so we do have losses associated with this. However, this current is not really the peak current. It's some value lower than that. So because of this operating mode, this type of amplifier can be designed to be extremely efficient. So switching related losses will be highly minimized with this type of operating mode. Now, if we take a really close look at the timings between the gate source voltage and the drain source voltage on an actual transistor, you will see that these two are not perfectly synchronized. So based on how the transistor is built, it will take some time for the transistor to start reacting to the variation on the gate source voltage, and it would also take some time for the transistor to fully transition between states. So the datasheets will normally cover this under 4 different parameters, which are all given for one specific use case. So you will be able to find the turn on delay and turn off delay, which is the time between when the gate source voltage starts varying and when the drain source voltage starts varying, so both on turning on and turning off states. and then you will find the rise and fall times, which relate to the time it takes for the drain source transition to complete. Now, the set of turn on delay plus rise time is known as the total of the turn on time, and then the turn off delay and fall time is known as the turn off time. Now, these parameters are a bit more difficult to highlight in the simulator on the basic switch model, but if you really need to simulate these parameters, then a proper transistor model will be most helpful. Now, we're almost done. However, there is one more particular type of loss that can occur in the MOSFET transistor, which might not be that obvious, since it's not occurring on the transistor itself, but rather the internal body diode. Based on the use case, usually when some sort of inductive load is involved, this diode can end up conducting and thus contribute to the total amount of loss occurring on the transistor. So this internal body diode is a PN type of diode, so there are two loss mechanisms in place. If we check the current running through this diode during a switching cycle, it will have this sort of a waveform, and the first loss is conduction loss, obviously, so when the diode is directly polarized, there is current running through it, and there's a certain voltage drop, so the conduction loss is the product of these two, so the diode current times the forward voltage. And the second mechanism is reverse recovery loss. So this is occurring because the diode ends up conducting the other way for a short amount of time when polarization is reversed. So the current from a direct value will go negative for a while and then go to zero when the diode is blocking. So this reverse recovery loss is occurring because of this reverse current. In applications implemented with half-bridge drivers like synchronous buck converters, the two transistors are driven in opposition. One is on when the other isn't. However, because the transitions are not instantaneous, and you do not want to run the risk of having both transistors running at the same time, in practice a so-called dead time is implemented, when none of the transistors is driven. This is when the body diode ends up conducting. So the body diode related losses are influenced on the one side for the conduction losses by the forward voltage, the dead time, and the switching frequency, so this happens every single switching cycle, and for the reverse recovery loss, it's influenced by the reverse recovery current, the reverse recovery time, and the switching frequency again. This effect can be highlighted on a synchronous switching converter. So I took the test fixture for this LTC3823 from the LTSpice library, and I replaced the switching transistors with some switches. And I also added a parallel PN diode to represent the body diode of the transistor. So if we run this simulation, if we first look at the gate driving voltages, so the signal going into the upper transistor, the signal going into the lower transistor, and we zoom in a bit, we can see that there is a very clear period in which none of the transistors are being driven. So this is our dead time. If we also look at the actual current going through the transistors, and zoom in to not see the various spikes, we can see that the current is also proportional to the driving signal. So there are these clear periods in which none of the switches are conducting current. However, if we also add in the inductor current, we can see that it's perfectly continuous. So there's no gap in the current running through the inductor. So the moment when none of the switches are conducting, this inductor current needs to go somewhere. And that somewhere is this low side diode. So if we zoom in, we can see that there is current running through this low side diode exactly when none of the two switches are conducting. So during the dead time, this internal body diode ends up conducting. Now, there's not much you can do about the losses associated with this diode, so all switching transistors will have this internal PN junction diode, which will have its associated losses. However, one thing that you can do is outside of the transistor, and that is to add an extra Schottky type of diode in parallel with this internal body diode. So the idea here is that since the Schottky diode has a lower forward voltage, most of the current that would normally go through the body diode would end up going through the Schottky diode. So if we check the same waveforms on the other circuit, so we have the same driving signals with a gap in between when none of the switches are conducting. If we look at the two diodes, so the Schottky one and the internal body diode, we can see that there's almost no current running through the body diode, and all of it is going through the external Schottky diode. So depending on the choice of this diode, you can reduce the losses associated with this mechanism. In the end, calculating the exact amount of loss that occurs on a switching transistor is not always a simple affair. But based on the application, certain sets of formulas should normally exist. It's important to observe, however, that there is not one single type of loss occurring, but many with multiple causes. And especially as switching speeds climb ever higher, the various switching-related losses start to become predominant over the conduction loss. And as with every electronic circuit, there is no one perfect component to use. The exact choice of transistor needs to be taken based on the specific use case that you have. And with that said, hope you got some useful information after this. Leave your thoughts and comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.